This podcast is brought to you by LMU Munich.
Okay, thanks very much. It's great to be here. I'll give you a lecture on supergravity. And what we call exceptional field theory. So supergravity, as you may know, is a very large subject, and there are many topics which one can discuss, and I suppose many of you have already heard something about supergravity and maybe others not so much. So what I'll try to do is to concentrate on various subtopics in supergravity, give you some ideas, show what are the typical structures which show up in these theories. But of course we cannot do everything in detail. I put some references for more details on this sheet which you have. And then if we have time, we will still come to discuss a little about these exceptional field theories. So the three big topics we'll discuss is what I will call basic supergravity, that will be really to introduce the concepts, to show you the simplest supersymmetric extension of general relativity. So here we'll see all the concepts of how to supersymmetrize the geometry of Einstein's general relativity. Then we'll come to extended supergravity. We will discuss theories which are more complex, which have additional matter, not just a metric and its super partner. So those are the theories which are really interesting in the context of string theory, for example. And then we'll have a third sort of complex of topics, which is gauged supergravity. That is where we will discuss how supergravity goes together with non-abelian gauge symmetry. And we'll see that many additional structures come in once we try to couple gravity not only to supersymmetry but also to non-abelian gauge symmetry. And then if we still have time after that, we may have a fourth discussion on these exceptional field theories. Which is a way to formulate supergravity theories such that all the exceptional symmetry groups which we will meet in the course of these lectures in fact turn out to be manifest. So that's roughly the idea of the course. You have a slightly more fine-tuned schedule on this sheet. You also have the references which I will refer to during these lectures. Okay, so let me start with a few very basic elementary remarks on supergravity. And of course, please feel free to ask questions whenever something is not clear. So what we mean by supergravity is theories which combine gravity, which combine supersymmetry, and typically some local gauge symmetry, which can be abelian or non-abelian. So let's just say local gauge symmetry, such as Young-Mills type of symmetries. And what we'll see in the construction of these theories is that once you impose these three properties of a theory to contain standard Einstein gravity, to be supersymmetric, and to have local gauge symmetry, that poses a large number of constraints on the possible interactions that you can write down. So in fact, there are only very few and very selected theories which have all these three properties. So this gives a highly constrained interactions. And maybe just a few keywords, why are we interested in such theories? I guess most of you have already stumbled upon some supergravity in some context, so it's not really necessary to give a lot of motivation. But let me just mention three sort of applications or appearances of these theories. So first of all, this of course, it combines gravity with supersymmetry. And as you know, supersymmetry in general improves the quantum behavior of a classical field theory. And gravity is a theory whose quantum behavior is, of course, very bad, as you know. Now, supersymmetry is presumably not sufficient to really turn gravity into a consistent quantum field theory. However, as you may have heard over the last years, in maximal supergravity, that is to say, a supergravity with a maximal number of supersymmetries realized, that is a four-dimensional field theory. It has 8 supercharges, the maximal number you can have in 4 dimensions. It has been constructed like 35 years ago. And until now, there's not a single divergence which people have found in that theory. So even though it's not really expected that this may be a finite theory of quantum gravity, today it's not excluded that this n equals 8 extension of general relativity could turn out to be a finite quantum field theory. Next, of course, one reason why we're interested in supergravity theories is that, as you probably all have heard, those are the theories which you obtain as the low energy effective actions in string theory. So in fact, for many of the applications of string theory, which you may have heard about, be it ADS-CFT, be it the study of flux compactifications, and so on, the tool which you use to do computations is the effective low energy theory, and that is the supergravity action. And the last item. Say this is the motivation if we believe in supersymmetry as kind of a fundamental symmetry of nature. But even if we forget about that, the very fact that Einstein's general relativity is a supersymmetrizable theory is already a remarkable fact. And in fact, is a very efficient tool if you want to study solutions simply of Einstein's general relativity. Okay. So simply for the study of solutions of, say, general relativity, matter-coupled general relativity, it turns out the fact that there is an underlying supersymmetric extension of this theory is a very efficient tool to construct solutions and to study their properties. So we may use this supersymmetry, in fact, just as a tool in order to study the bosonic theory, which they underlie. Okay, so that's just a few words of motivation. Let me put together a number of basic properties of supergravity, or supersymmetry first. Well, I guess all of you have heard about supersymmetry, of course. Supersymmetry, which exchanges bosonic and fermionic fields. Schematically, it's a symmetry such that if you vary a bosonic field, it turns into its fermionic superpartner. So you will have some bilinear combination. It's really very schematic. We will put details in the following. So the variation of bosonic field is its fermionic superpartner. In order to make this a well-defined transformation, you have a symmetry parameter epsilon, which is the fermion itself, the supersymmetry parameter. And in turn, the variation of the fermionic field in general carries the derivative of the bosonic field and the supersymmetry parameter. Okay, so bosonic and fermionic fields are exchanged. There's a space-time derivative which shows up here, which you see from simple well, if you look at the dimensions which fields carry, say in 4 dimensions, dimension of a bosonic field is 1, dimension of a fermionic field in 4 dimensions is 3.5. So you see that from such a transformation law, you need a supersymmetry parameter whose transformation is just -1/2. And so you see, in order to make this work out with the dimensions, you need something else which carries dimension on the right-hand side. This is 3.5. This would only be 1/2. The only object which carries dimension is a derivative. So that's roughly the structure of any supersymmetric variation, from which we see already a simple fact. If you have global supersymmetry and you study the algebra of 2 such transformations, again, everything is very schematic, and we will put details and indices in the following. But roughly, if I consider a commutator of 2 such supersymmetry transformations, say on a bosonic field, well, there will be a second variation of this variation. So it will basically carry epsilon bar to, well, let's say proportional. Okay, there will be details missing. There will be the derivative of the bosonic field and then the other fermionic parameter. But what is this? This is nothing but, if I spell out the gamma matrix, some vector field, which is a fermionic bilinear of the 2 supersymmetry parameters, multiplying the derivative of this. And what type of symmetry is this? This is just translation in the bosonic field. So that's something you probably have heard about. Supersymmetry closes into translations. Okay, the commutator of 2 symmetries should be a symmetry. The commutator of 2 fermionic symmetries should be a bosonic symmetry. Typically, there's not an infinite number of bosonic symmetries that you can invent, and one of the typical ones are translations. So when you have a globally supersymmetric theory, it is a theory which is necessarily also invariant under translations. Now, that becomes more interesting when we look at local supersymmetry. So imagine we have a theory which is supersymmetric with a supersymmetry parameter epsilon, but it's supersymmetric for any function epsilon of x, any space-time function epsilon of x. Imagine we are able to write down an action such that the action is invariant under such type of symmetries, but now epsilon is an arbitrary function of x. Well, if that is the case, we still can look at the algebra of two such transformations. Again, let's not go into the details of indices and all, but what we see from the structure is now the commutator of two local supersymmetries. Well, the structure remains roughly like that, except for now epsilons are space-time functions. So the commutator of two supersymmetries will be some vector field. This is my vector field, psi. But now a space-time dependent vector field multiplying d mu of b. So what's that? That's a local translation. It's a translation in direction of psi, but psi is a vector field which is space-time dependent. So that is the infinitesimal action of a diffeomorphism, of a coordinate change. So the algebra closes into diffeomorphisms. So that means if we manage to construct a theory which is invariant under local supersymmetry, that will be a theory which is also invariant under diffeomorphisms. Okay. Now I guess well, for sure you have all seen some globally supersymmetric models like the Wess-Zumino model, where you construct like free field interactions and so on, maybe some interaction terms. Imagine we can turn that into a locally supersymmetric theory just by this simple argument that locally supersymmetric theory will be invariant under diffeomorphisms. And there are not so many theories which are invariant under diffeomorphisms, so typically these theories include gravity. And in particular include some dynamical background metric to which the fields couple. And in fact, you could play that game. You could say start from your favorite supersymmetric model, take the Wess-Zumino model. You try to make it invariant under local supersymmetry, as you do in electrodynamics when you make the U1 local and you come out with gauge theory. You can start the Noether procedure, which turns, say, the Wess-Zumino model into a supersymmetric field theory, into a locally supersymmetric field theory. But unlike electrodynamics, it's a Noether procedure which will not stop after adding the first correction term. Okay? It will need, in fact, an infinite number of correction terms, which is not surprising in view of that result, because what you do by that construction is you reconstruct general relativity. Just you do it in some perturbation expansion in which you have an infinite series to some. So it's not the most efficient way to construct general relativity. Okay? But conceptually, you would be able to reconstruct all of Einstein's general relativity simply by making such a model locally supersymmetric. Okay? So just the upshot is local supersymmetry, a theory which has local supersymmetry, is what we call a theory of supergravity. Because necessarily it includes gravity. Let me just add one more remark. So how do we turn a theory which has a global symmetry into a theory which has a local symmetry? Well, we need to introduce a gauge field. Again, as you do in electrodynamics, when you make the U1 local, you need to introduce a vector field with its interactions and the minimal couplings to the matter in order to make all your theory locally symmetric. Now here, we're talking about a symmetry whose parameter is a fermion. It's the epsilon. So in fact, this gauge field itself will be a fermion. So it will be an object which looks like a gauge field. It's not the A mu, it's say like a psi mu, but it's itself a fermion, which means in addition to that space-time index, it carries also, say, a fermionic index alpha. Such that its variation under supersymmetry is just given by the space-time derivative of the supersymmetry parameter. Okay. Just as for U1, say, you introduce a vector field whose variation is just the derivative of the symmetry parameter. Okay. So here I put explicitly the spinor parameter epsilon. In the following, I'll often just suppress that, and we will just think of epsilon as a spinorial object living in some spinorial space, and the same for psi. Okay. But I will always spell out the space-time indices. So the vector field is a field of spin 1. This is a field of spin 1 times the spinor space, which is spin 1/2. So this is in fact a field of spin 3/2. And that's the field which is called the gravitino. And it will play the role of the superpartner of the metric, which itself is spin 2. Of the metric, say G mu nu. Of spin 2. Okay. That was the general remarks. Now I'll do the same in some more detail. Okay. So now we'll really try to construct what we can call basic supergravity. We have seen that the moment we want to write down a theory which has local supersymmetry, we need to include gravity. So the simplest theory we could think of is just a theory which looks like general relativity, say, the Einstein-Hilbert-Lagrangian. Okay, let's be more specific. Einstein-Hilbert-Lagrangian in my conventions would be minus 1/4 the Ricci scalar plus, well, some supersymmetric extension. presumably carrying this super partner of the metric. Such that the full theory is invariant under some supersymmetry transformation of that kind sketched up there. Okay, so that will be the first goal. Construct the supersymmetric extension of general relativity. If there are any questions so far. Okay. Well, let's try to construct this interaction term, well, the coupling of the spin 3/2 field. That will be the coupling of a spinor to general relativity. And the way to make spinor fields show up in or coupled to general relativity is by introducing the tetrads of general relativity, the field-bound formalism. Okay, so we need the tetrads field-bound formalism. I'm not sure if everybody has. Is everybody familiar with the field-bound formalism of general relativity? In any case, I'll just summarize the formulas which we need. Okay, so if you have not seen them, try to digest them. So we need to introduce the tetrads, field-bound. Instead of the space-time metric G mu nu, we will work with these objects E mu A, E mu B, contracted with the Minkowski metric. And for most of the lectures, I'll use a signature plus, minus, minus, mostly minus. So the tetrad is the object which translates the curved space-time index into a flat Minkowski index. It is defined up to local Lorentz transformation, which leaves eta invariant. So there's local Lorentz symmetry manifest. Under which the field-bound just does a rotation from the right with a matrix lambda which lives in SO 1,3, the Lorentz group, or the algebra of the Lorentz group. But the Lorentz group also acts on the fermions, as you know, by minus 1/4 lambda AB gamma AB fermion. So if there's local Lorentz symmetry, in order to have such a symmetry realized on the fermions, we need also covariant derivatives for the fermions. We need a gauge field which makes the theory invariant under local Lorentz transformation, and that gauge field is the spin connection. So in fact, we will define covariant derivatives on fermionic fields as follows. d mu f plus 1/4 omega mu, that's the gauge field, the so-called spin connection. It lives in SO13, so it carries two indices AB, and it's antisymmetric in those two indices, and it acts just like a Lorentz transformation on the fermionic field, gamma AB F. Okay. And this is what is called the spin connection. And that is not a dynamical gauge field itself, as it would be in electrodynamics. It's what is called a composite connection. It's a function of the tetrad field. Of E mu A. And it's a function such that the tetrad itself is covariantly constant, such that d mu E nu A is 0. And what do we mean with this covariant derivatives, just to be clear? Well, there's this connection inside this covariant derivative acting on the flat index, AB. But we are in general relativity, there's also the Christoffel connection acting on the curved spacetime index. Minus gamma mu rho A. With the Christoffel connection, which is a function of the metric and its derivatives. Okay, so that is an equation from which you can determine the spin connection. Or you can do simpler. You can just take a contraction of that equation onto its antisymmetric part. Let's project this equation onto its antisymmetric part in mu and nu. Well, if we don't have torsion, the Christoffel connection, as you know, is symmetric in its two indices. So when we project this equation onto its antisymmetric part, the Christoffel connection drops out. So a simpler sub-equation from here is just the antisymmetric part, which we can write like this, d mu. But now it's a d mu which only carries omega and not the Christoffel connection. E nu A is 0. Antisymmetric, by these brackets I always mean antisymmetry, antisymmetrized in mu and nu. That's a simpler equation in absence of torsion. That's a simple equation because we don't have to worry about this Christoffel symbol and its definition in terms of the metric and so on. It's an equation which only carries the derivative of the tetrad and the spin connection. And it turns out this equation you can solve for the spin connection, and that gives you the standard formula for the spin connection. And I'll just give you the result. If you solve for the spin connection, you get omega mu AB given by minus 1/2 E mu C. Expression is slightly lengthy, but well defined and unique. Okay, it's a combination of 3 capital omegas, and the omega is what is called the object of unholonomity. Object of unholonomity, omega ABC. It's twice A mu EB nu. The derivative of the tetrad. Okay, you plug that in, you have the expression for the spin connection as a function of the field line. Question? Yes. Why is it called that way? The object of I don't know. I don't know. Okay, so that's the spin connection. It's a connection. Every connection has a curvature. That's kind of the invariant object which characterizes the connection. And the curvature of omega is the Riemann tensor. So if you calculate, remember it's a connection which lives in the algebra SO1, 3. So its curvature is defined as the curvature, as a Yang-Mills curvature of an object living in the gauge algebra SO1, 3, twice d mu omega nu AB. By these brackets, I also mean antisymmetrization. Okay, sometimes I put these brackets, sometimes I underline like that. It's antisymmetrization, always with a weight 1, plus twice omega mu AC nu CB. That's the Riemann tensor, which means if we take the Riemann tensor of general relativity, which you know how to compute in terms of the Christoffel connection, and you turn these two curved indices into flat ones, by using the tetrad, the result is nothing but the curvature of the spin connection. Okay, so either way you compute the curvature, either of the spin connection, either of the Christoffel connection, the result is the same. And that's not a miracle, that's just a consequence of the fact that there is a covariantly constant object, which is the Vielbein itself. Okay. If you have a covariantly constant object, and if moreover this object is an invertible matrix, then of course also the commutator of two covariant derivatives on that guy is 0. But the commutator of two covariant derivatives is the curvature. And now is one piece of the curvature acting here and one piece of the curvature acting here. And one will be that curvature from the Christoffel connection, and that will be the curvature of the spin connection. And the difference between the two will be 0. Okay. And so the standard Einstein-Hilbert action will just be minus 1/4 determinant of the Vielbein, which is a square root of the determinant of the metric, and then simply the Ricci scalar obtained by contracting the Riemann tensor. Which is the curvature of omega, and omega itself is a function of the tetrad. Okay. So here's a formula which is useful for the following. Computing the variation of that action gives a very simple expression. If we vary this expression with, you can't really see it, if we vary this with respect to the tetrad, of course there are some easy terms which are just varying these algebraic dependence or appearance of the Vielbein. But there's also, of course, the omega, which depends on the tetrad and its derivatives. So if you vary the full Lagrangian with respect to the tetrad, a priori, that's a complicated expression. But the result is very neat. It is just minus 1/2 times the Einstein field equations. Of course, that's how it should be. If we vary the Einstein-Hilbert action, we should find the Einstein field equations times the variation of the inverse tetrad. Okay. If you've never done that, that is a nice exercise, a nice small exercise. To reproduce this variation from that form of the action. Okay? To really prove why the Einstein-Hilbert Lagrangian, which is just the Ricci scalar, in fact gives the Einstein field equations. Okay? And in that form of the action, that's maybe the most compact way of showing it. And we will, of course, need this expression because we want to study supersymmetry of the action. So at some point we need to talk about varying the action, and this is the variation of the Einstein-Hilbert part of the action. Okay, any questions? Yeah?
I was just wondering how you learn raised in
Oh, yeah, good point. Well, all indices on any object I raise and lower with the corresponding metrics. So say the flat index I raise and lower with the Minkowski metric, and the curved index I raise and lower with the spacetime metric. Okay, which means for the Vielbein, it means in particular, for example, E mu A. Let's take this object which written there, that would be G mu eta AB E mu B. Okay, having raised and lowered the indices with the metrics. But, moreover, this guy is nothing but the inverse Vielbein, okay, which follows simply by plugging this in. So, actually, E mu A times E B mu is nothing but delta AB. So, you could say on the Vielbein, either I use it by defining it as the inverse, or I do it by raising and lowering the indices as I do on any object, but the result is the same. Other questions? Okay? Good. So that was the bosonic part of the action. Now just in the Vielbein formalism, in which we know how to couple spinors. So next, we can worry about how to couple that spinorial field, the spin 3/2 field, which we know will appear as the superpartner of the metric. And that goes under the name of the Rarita-Schwinger action. So the challenge is just to find an action for this field psi mu, which is a field of spin 3/2. So it's a fermionic field. We are looking for something like the Dirac action of a spin 1/2 field, but generalized to this object which also carries the spacetime index. Now that's something which has been written down long time ago, much before supersymmetry was invented in the 40s by Rarita and Schwinger. In 41. And the action they give is the following. 1/2 in 4 space dimensions, space-time dimensions. A, B, C, D, psi bar A, gamma B, gamma 5, derivative psi D. So this is 4 space-time dimensions of the. At the time, of course, people were only thinking about 4-dimensional field theories. It's in flat space. So this is really like quantum field theory on 4-dimensional Minkowski space for a field of spin 3/2. Of course, what they had in mind was not an elementary spin 3/2 field, but more like a composite object, and trying to write down a Lagrangian for that. And it turns out this is the one which gives the right dynamics. Well, this is on flat space. First thing we need to do is put this on a curved background, because we want to couple it to gravity, but that's easy. We know how to do that. Basically, all we have to do is put all these indices into their curved analogues. So for us, the spin 3/2 field will couple as follows. Coupling to general relativity. One half epsilon mu nu rho sigma sidebar mu mu gamma 5. And next, of course, here we have a partial derivative. Now the index will become a curved index, but we have seen that in order to make theories locally Lorentz invariant, we have to covariantize all the fermionic derivatives. So in order to couple this to a dynamical metric, this will become a Lorentz covariant derivative. D rho, this will be precisely carrying our spin connection, then acting on psi sigma. Okay, so that's the answer for how to couple a spin 3/2 field to curved background. Yes?
What's the convention for the epsilon symbol on the curved space?
Yes, what is the convention? Good question. What is the convention for this guy? You'll find in the various texts and books, everybody uses his own conventions for this thing. So what we will use here is this epsilon, when I write it as a sort of curly epsilon, it's not a tensor, it's a density. Okay, so this is a density. It's just the numerical it's a number. So epsilon 0, 1, 2, 3 is just +1. Okay, so there's no field dependence in here. But as a result, it is not a tensor, but it transforms as a density, which you can see as follows. Of course, you all know the object on flat space, the Levi-Civita tensor. That's a Lorentz tensor. That's a truly tensorial object. So if I multiply it with, say, 4 vielbeins, this is still a tensor, because it's nothing like the product of 5 different tensorial objects. This is a tensor, okay? But this is a number, and this is a matrix. This is 4 times the same matrix, anti-symmetrized in the 4 indices, so the result will be proportional, again, to a number, epsilon mu nu, totally anti-symmetric. Okay, so remember, this is a number, but since I multiply these 4 matrices, there will be a factor, which is the determinant of that matrix. Okay, that's nothing but the, and since this is the inverse tetrad, this will be the inverse determinant. Okay, so this is numerical. This is numerical. This is nothing but the definition of the determinant, if you wish. I take the matrix, I anti-symmetrize in all the indices. I get again a number times the determinant. Okay. But since this is a tensor, this is a tensor. So this object, which is numerical, times the inverse determinant is a tensor, which means the object itself is a density, or transforms as a density. Okay. Now, in some texts, you will see that people call this object, which is a tensor but not a numerical object, the Levi-Civita tensor, and they will call that epsilon and so on. Okay. For me, the epsilon always is a density itself. The purely numerical thing. Okay? And that is why there is no factor, density factor in front. Okay? Because this guy already is a density. Other questions? Okay. Just one more remark. If you look at like that. Of course, this is a purely four-dimensional definition. There's the epsilon density, which is a four-dimensional object. And of course, at the time, people were only interested in four space dimensions. But what we will, of course, ask for later is also supergravities in other space-time dimensions. Then this definition, of course, doesn't make much sense because the gamma 5 is a four-dimensional thing. That's a four-dimensional thing. So we'll need an equivalent way of writing this action, which is the following, which you find after just a little gamma matrix algebra. Epsilon times the gamma matrix is nothing but a threefold antisymmetric product of gamma matrices. So I can write this equivalently as a gamma mu nu rho d nu psi rho. In four dimensions, that's exactly the same thing. Remember that gamma 5 was nothing but I, gamma 1, gamma 2, gamma 3. Okay. Now that's a definition which you can formally write in any space-time dimension. As soon as you have spinors with certain properties and so on. But formally, there's no restriction to the space-time dimension here. Okay? So when we talk about supergravity in other dimensions, this will be the corresponding coupling of the gravitino field. Yes?
Isn't it useful to keep the gamma 5 for chirality purposes?
That will depend on the particular theory we will be looking at. So indeed, when we write, when we start constructing four-dimensional theories, it may be useful to keep that. But of course, in other dimensions, we don't even have the gamma 5.
I mean, you could use some kind of chirality matrix, right? And it's always defined.
If I'm in even dimensions, yes. Yes.
In odd dimensions, you can also sort something out, right?
In odd dimensions, I don't have the analog of that gamma 5. In even dimensions, in fact, sometimes it will be useful to put the explicit gamma 5. Sometimes it will be useful to go right away to a basis of spinors, which is a Weil basis, in which the spinors are already chiral, and so all the gamma 5s will disappear because they act already as plus or minus 1. And that will depend on the particular theories we'll be looking at. Okay? So here, actually, I haven't really introduced my spinor. Maybe I should say you the spinor conventions. That's a good point. At least in four dimensions, we can still be precise. Spinor conventions. As you know, in four dimensions, we have the choice. We can go to chiral spinors, to Weil spinors, or to Majorana spinors, where we impose a reality condition. We cannot have both. Now, this action up, where is it? This action up there is written for a Majorana spinor, which is a spinor which satisfies a reality condition. Majorana spinor. And it satisfies the following. So the Dirac conjugate spinor, which is defined in the standard way as the adjoint times gamma 0. We ask this to be the same or related to the transposed times the charge conjugation matrix. Okay. So in other words, the complex conjugate of the spinor is related to the spinor itself, which means on all the spinor components you impose some kind of reality condition. And so in fact this is not a spinor of 4 complex components, but it's parameterized by 4 real components. And the charge conjugation matrix in 4 dimensions satisfies some properties like this. C times C transpose is minus the identity. That's the same as C times C star. Okay. And that's why gamma 5, for example, acting on this on the Majorana spinor is just a new object. So lambda and gamma 5 lambda are just like 2 different spinoidal objects, and so gamma 5 in the action is an important object. Whereas if we go to a basis, to a complex basis of chiral spinors, the gamma 5 would always act already as plus or minus 1 on the spinors. Okay? Okay. So we have coupled the spin 3/2 field to background metric. So as for our supergravity action, at the moment we are here, we have the Einstein-Hilbert term. We have the Rarita-Schwinger term. But it would be very optimistic to think that this could already be supersymmetric. This is just like a kinetic term for the spinor. Of course, in principle, we would also expect some kind of interaction term for the spinor. Remember, this is general relativity. It's not a free theory. It has an infinite number of interaction terms if you would spell it out. So there's no reason to expect that for the spinor it stops here just with a free kinetic term. Okay, so presumably there's some kind of phi to the 4 or maybe even psi to the 6 and whatever interaction terms in order to make all this into a supersymmetric theory. Okay. It's unlikely that the supersymmetric partner of a highly interacting theory is just a free theory of a spin 3/2 field. Okay? And indeed, that's not the case. Still, we can first check if we are on the right track, if this action we have been writing down, at least to lowest order, is the supersymmetric partner of the spin 2 part, of the Einstein-Hilbert part. And that's very useful to check. In order to do that, well, we should first have an idea. How do our fields transform under supersymmetry? Okay, so what is the supersymmetry transformation law of the 2 fundamental fields, which is the Vierbein and the spin 3/2 field? Well, how to figure that out? Remember, we had kind of schematically the general form of how fields transform in supersymmetric theories. So, for example, a bosonic field should simply transform into the product of the supersymmetry parameter with a fermion. Well, there would be an epsilon together with this psi mu. Plus, we have to respect the index structure, so we need to have the right behavior under diffeomorphisms and Lorentz transformations. If you think about all that, there's not much, in fact, you can write down, say up to factors. Okay, there's a minus I just for the reality properties of these spinors, because of course we want that the variation is a real thing just as the field line itself. An epsilon bar, gamma A, psi mu. Okay? If you think about it, that's more or less the only thing you can actually write down here. If you don't write something in higher order of the fermions. Okay? It carries one epsilon, it should carry one psi, be linear in both, have no derivatives, and have the right index structure. The only object which can carry an index is a gamma matrix. So what else could it be? Well, and the gravitino field itself, remember, it should be something like the gauge field of supersymmetry, so its variation should be the derivative of that supersymmetry parameter. And now, since we're in general relativity, that derivative, of course, will be a covariant derivative, a Lorentz covariant derivative acting on this supersymmetry parameter. And that's all. And maybe, okay, maybe plus higher order fermions, we could say, for both. Let's not worry about the higher order fermions for the moment. We come back to that in a moment. Let's just see if to lowest order this has a chance to work out. Okay. Well, useful thing to check is what is the algebra of such transformations? If you start constructing supersymmetric theories, it's very easy to get lost because you try to construct an action. So you start from two terms. We don't know what this fourth term is. What could it be? We could guess something. But at the same time, you start constructing what are the supersymmetry transformations. So you can play around here, change coefficients, terms, couplings, but you can also change the supersymmetry laws. Okay? And in the end, all should work together. This action should be invariant under those transformations. Okay? But if you start playing at too many parameters and structures at the same time, it's very easy to get lost. So a more systematic way of approaching things is, let's first look at the algebra. Because whatever we write here as a transformation, if I do two of them, and I do the commutator, that should be a well-defined algebra of symmetries. So if I do a commutator of two such transformations, I should find a bosonic symmetry. And again, bosonic symmetries you don't invent like that. Bosonic symmetries will be diffeomorphisms, Lorentz, and maybe some gauge symmetry. Okay. And that's totally independent of what the action may be. So we can, for the moment, completely ignore this. Anyhow, we don't know what it is. Okay. We just look at the transformation laws. We check if their transformations are at least close into an algebra. That's a good check. Okay. So let's do that. That's a neat standard calculation. What is the commutator of two supersymmetry transformations on the field line? Well, that's not so complicated. Okay. First transformation gives us this, and the second will just vary psi into this derivative. So I find myself with minus I epsilon bar 2 gamma A, and then d mu of epsilon 1. And then I should subtract 1 and 2 interchange because it's a commutator. But the thing with 1 and 2 interchanged has the derivative acting on epsilon 2. And so the combination of the two is nothing but a total derivative. It's minus I d mu of this guy. We use that for the gamma matrix between two spinors. For Majorana spinors, you can interchange this with a minus sign. Okay, so we have some pretty compact result. It's the derivative of what we could call some vector field psi A. Psi A being minus I bosonic vector field. Now what's that? What kind of symmetry is this? If my Vielbein transforms into a derivative of something, well, what do we expect? A Vielbein should transform as a diffeomorphism and maybe as a Lorentz transformation. This is not yet a diffeomorphism. It's not yet the action of a diffeomorphism, but actually it comes close. Let me rewrite it a little. This is nothing but a diffeomorphism is parametrized by a vector field with a curved space-time index. So that would be a true diffeomorphism parameter. Well, that's nothing but having changed, well, I translate the flat index into curved index. I have the derivative now acting on psi and on the tetrad, but it's a derivative which is covariant with respect to the spin connection. Which means if I act on the psi parameter, there's no connection term. And if I act on the second, on the tetrad, it will just be the d omega mu on E mu A. Now we get closer to something which looks like a diffeomorphism. In fact, this would be the first term of a diffeomorphism if the two indices were interchanged. You would simply have psi nu, d nu on the Vielbein, like the translation term of a diffeomorphism. Well, but we can exchange the indices, because remember we had that equation a while ago. If I act with a covariant derivative on the tetrad, and I antisymmetrize in the two indices, the result is 0. So in fact, this is nothing but, I just copy the first term. I interchange the two indices, because we don't have torsion, plus psi nu d nu E mu A. And all that I'm left with is the spin connection piece, which is psi nu omega nu AB E mu B. And that's perfect. These two terms are precisely the action of a diffeomorphism on a curved index. See, translation term plus the conjugate term. And what is this? Well, this is like a matrix AB acting on the right. This is a Lorentz transformation with a particular parameter. Okay. So things are fine. We have shown that the algebra of supersymmetries on the Vielbein closes into a diffeomorphism and a Lorentz transformation. Both are bosonic symmetries of our action, so this has a chance to work. Well, now we have to make, so that's a good first test, so we know that these transformation laws are not totally weird. Now we have to check that the action is really invariant under this. And that is now a very easy calculation. Now let's look for the variation of the action. Variation of the Einstein-Hilbert term. We had that transformation, that variation a while ago. That was the formula I was giving you. It is still up there, I think. The general variation of the Einstein-Hilbert action. Now simply we plug in the explicit variation of the tetrad. And so the result will just be I over 2 density R mu nu, the Einstein equations, times psi bar mu gamma nu epsilon. Okay. I've just used this to interchange the order of psi and epsilon that makes up for sign here. That is the variation. So what we need to compute now is the variation of the Rarita-Schwinger action. Okay? This is the variation of Rarita-Schwinger. Well, there's two gravitinos, one to the left, one to the right. But the variation of both terms gives twice the same contribution, as you see by partial integration. So we'll just have a minus I E psi bar mu gamma mu nu rho d nu d rho on epsilon. Okay. Remember the Rarita-Schwinger action just had a psi rho here, and this is the variation of psi, and that's all. Now, of course, you may wonder, there's also, for example, this determinant in here, which will vary. There are curved gamma matrices here. There's some field-bound dependence, of course, in this expression that will vary, and so on. But all those terms will give higher order contributions to the fermions. Because I'm already bilinear in fermions here, psi psi. If I vary this, I will get another psi epsilon, so I will be at order psi cube. Okay, so to lowest order in the fermions, this is the only contribution. And let's first see that it works to this order. Well, the structure is nice. There's two covariant derivatives antisymmetrized, so this is the commutator. So this is the curvature. So that's a Riemann term. That's good because it starts talking to the Einstein-Hilbert term. Okay, so if we be more explicit, this is the curvature acting on a spinor. So it will be I over 8. It's 1/2 the curvature, because it's 1/2 the commutator. E psi bar mu. I just copy. And now the curvature acts by product of two gamma matrices R nu rho sigma tau. Okay, that's all. So we have some spinorial expression with gamma matrices and so on, and then just the Riemann tensor. Now all we need to do is develop this product of gamma matrices, a gamma 3 times a gamma 2. Now you know from quantum field theory, but it's true in any dimension, a product of gamma matrices, you can always expand it into monomials of purely antisymmetrized gammas. Okay? So the gamma identity we need is the following. This is gamma mu nu rho sigma tau. This is the guy totally antisymmetric in all 5 indices. And then there will be gamma 3 and a single gamma term. Okay? And all the non-trivial input is the factor in front. And that you have to find by, say, contracting the identity or something. This is 6 times gamma mu nu tau delta rho sigma antisymmetric, and then 6 times single gamma delta nu is tau and rho is sigma. Okay, just expanding product of gammas into single monomials. And if you're not sure about the factors, just compute some traces, contract this, say, in rho and sigma, and that will bring things down to single identities, and you can derive the factors in front. Okay, now what happens? Well, this is a gamma antisymmetric in 5 indices. In 4 dimensions, that's absent. Nothing can be antisymmetric in 5 indices if we have only 4 of them. But let's keep it for the second, because we'll see that calculation actually goes in any space-time dimension. So in 5 dimensions, this would be non-zero. This would just be the epsilon tensor in 5 dimensions. Then we have this guy, and then we have that guy. Now what happens? Well, we have like 3 different contributions, and they all contract the Riemann tensor. Let's look for the first one. There's a totally antisymmetric gamma here, and it multiplies this R. And it contracts 4 of the indices, nu rho, sigma, and tau of the Riemann tensor. But the Riemann tensor, as you know, has a few symmetry properties. In particular, the Riemann tensor satisfies this Bianchi identity, just as a consequence of its definition, if there's no torsion. Everything I say is without torsion. Okay? This is 0 simply by definition. It's the Bianchi identity. So it means whenever I contract R and I antisymmetrize in more than 3 indices, in 3 or more indices, the thing just doesn't contribute anything. Okay? So this guy, in fact, it doesn't contribute anything. Well, the choke also doesn't contribute. Okay, this gives no non-trivial term. And also some of the others will vanish. For example, here, imagine, well, we should write out all the different combinations where we anti-symmetrize indices, but imagine nu and rho are both on the gamma. Okay, then I have a gamma with nu, rho, and tau, and that will contract 3 indices of R, and that also gives no contribution. So in fact, only very few terms survive. And let's spell them out. From here, only like 2/3 of the terms survive, namely when I have mu nu or mu rho. Okay. Minus I over 8. I just copy that. Psi prime mu. And now we just spell it out. Well, there's a mu, gamma, mu, nu, tau, and it multiplies nu, rho is sigma, sigma tau, and all that with a factor of 4. That is all what comes from here. But what is that? Well, this is the Riemann tensor contracted over 2 indices. That's the Ricci tensor. But the Ricci tensor is symmetric in nu and tau. And this is antisymmetric, so this also is absent. See, most of the terms just do not give you anything. Okay? So in fact, the only non-vanishing contributions come from here. Well, let's spell them out. Depending on where mu is, there will be 1, 2, 3 different terms. Let's take the first ones. That makes us a minus I over 4 E I times E times psi bar mu gamma mu epsilon, and R mu rho, and sigma tau is just contracted with tau sigma. And then we have twice the term where I do a rotation on the indices. It's psi bar mu, gamma nu, epsilon, R mu rho, and now sigma is mu, and tau is rho. Okay. I hope we didn't make a mistake, but it looks good. Okay, this is what? This is nothing but the Ricci scalar. The Riemann tensor totally contracted. This is minus the Ricci scalar. And this is what? This is the Riemann tensor. The Ricci tensor. Okay, so we are left with minus I over 2, determinant psi bar mu gamma. I bring the index down. Mu, and then we have R mu nu minus 1/2 G mu nu R. Okay. And that's just the inverse of what we found for the variation of Einstein-Hilbert. So in lowest order of the fermions, everything is 0. It's a good point to stop. But let me just the nice thing which we see here is that sort of the Einstein equations, or that variation which is proportional to the Einstein equations, in fact comes from some gamma matrix identities. Okay? So it comes from some structure on that spinorial space. By expanding gamma matrices into different bases, working out the indices and so on, we come to that very same combination. Naively, we could have found a different factor here, a different contribution or whatever, but it's exactly the Einstein equations. Okay? So that is a non-trivial property, if you wish, that's a non-trivial property of general relativity, that there is some spinorial structure behind, which sort of makes it supersymmetric. So let me just finish with a few remarks. So we have seen that the Lagrangian of supergravity is 0. The variation, sorry, not the Lagrangian. It's 0 to lowest order in fermions. And if you think about it, if you look at the calculation, in fact, at no point we have used that we're in 4 dimensions. If we use the proper form of the Einstein, of the Rarita-Schwinger term. So this is true in all dimensions, in fact. Well, we have used some of the reality properties of the spinors. Okay, so it's true in all dimensions where you have proper spinors, Majorana spinors, say. But even in the others, you might have to just add the complex conjugate. It will still work out with proper real spinors. Say. Just a final remark. In general, this fails, of course, when we go to the interaction terms. Okay. In general, and that is where we are really, where supergravity is really selective. And we will find that only very few theories, in fact, exist. And the fact that the theory is supersymmetric to all orders and fermions is a highly non-trivial result. Okay? In general, fails at psi 4. Only true for very selective theories. And of course, the calculations you have to do to check things at higher order than the fermions are far more complicated than the ones I've been sketching here. Okay? So we'll not do any of those higher order fermion calculations. I'll just give you a few results in the next lecture for very selected theories. Okay. So we'll see supergravity theories only exists in very few cases and with very particular properties, and those are the ones we're going to study. Okay, I think it's a good point to stop.